All right, we are continuing on. I am about to now teach about the frictional inclined plane, an extension to the previous lesson, which was the frictionless inclined plane. Now we need to talk about modeling motion along an inclined plane, and maybe even scenarios where there is no motion. It's enough friction where you put it there and it just stays there. But we need to learn how to model and incorporate concepts of friction, conceptual ideas, as well as mathematical ideas into this discussion about inclined planes. So I've drawn this as a little rough, a little jagged to indicate that there's some roughness there. This is not the frictionless inclined plane, frictional. Well, let's just, before we come to this, let's just remind ourselves a little bit about what we've done at this point regarding friction so that we can more quickly pull it into this new discussion about inclined planes. Remember that if something is sliding, and that's actually the first type that I'm going to talk about, there'll end up being two discussions. One is static friction, and the other is kinetic sliding friction. I'm going to actually start with the kinetic sliding friction case and talk about that, and then maybe I'll do another lesson on static friction. They're actually similar, but I'm going to start here. Imagining that this thing is sliding down a frictional surface. So let's just imagine the same idea, just flat, right? Just because remember that although the inclined planes look more confusing because they're inclined, you can just turn it and reduce it to something you're familiar with, which is something moving on a flat surface. Right? Well, and we'll do that in a moment. So my point is, let's just imagine there's a block here, no gap like it's showing that it's connected. You know, it's in contact, and it's sliding along, sliding and moving in this direction with a velocity to the right. And this is considering that this is a frictional surface. All right, in which direction would the frictional force be? Always opposite to the direction of motion. It's a resisting force. It's an opposing force, a retarding force. So they're all words used in physics to describe a force that resists motion. It doesn't help motion. It doesn't promote motion. That would be a force either directly in the direction of motion, or with some component in the direction of motion. But this is entirely a force that's always directly opposite to the direction of motion. So we know it's going to be a force to the left. This would be our free body diagram. This would be the friction force, right? We did this already. We know there's some other forces at play. We know that there's the gravity force, its weight pulling down. And we know that the normal force must balance this gravity force out because it's not moving up and it's not moving down, it's just moving straight to the side, right? So the normal force in the upward direction is equal in amount to Fg. Normal force, remember, is just the amount of force that the surface that it's at rest on is providing pushing back up into the object to support it, to prevent it from falling due to its own weight. Right? And so if this was the sliding, this is sliding scenario, and someone said, what is the amount of frictional force or magnitude of the kinetic friction force, which we know is to the left? Well, remember that it's a percentage usually, as long as the coefficient of friction is less than 1, then you can consider it to be the frictional force, the sliding frictional force, some amount of force that's less than what the object weighs. It's a percentage of the weight of the object. And we'll get to that more specifically. But right now, this is the coefficient, remember, the coefficient of kinetic friction. The symbol is called mu, K for kinetic friction, the coefficient of sliding friction or coefficient of kinetic friction. But we wouldn't put S here for sliding because that would be confused with mu S, which is for static friction. So we use the word sliding sometimes to remind ourselves that that's what kinetic friction is, sliding effect. We wouldn't use the S here for sliding effect, sliding coefficient. And it's always equal to this coefficient times the amount of normal force occurring in between the two surfaces. In magnitude, there's some amount of total force in between here because it's a block and it's sitting on the surface and it's pressing down, right? There's a normal force downward on the surface. The surface itself feels a downward normal force from it, and it feels an upward normal force from the surface. Those would be equal in direction, in magnitude, but opposite in direction. But we're never really usually interested in the surface. We're interested in the moving object. So the normal force is up, right? But remember that it's equal to mg. Both of these, at least in magnitude, in amount, opposite in direction. You could call this negative mg if you're interested in the direction, but in amount, in quantity, they're both equal to mg. So in this simple case, the simplest case of something just sliding nicely on a flat frictional surface, there's no additional forces pulling it, pushing it in an angle or lifting it or anything else crazy happening. It's just a book sliding across the surface of a floor. Then we can say that this is true. Fn is equal to mg. And therefore we can just plug in mg here and say that the amount or magnitude of friction force, sliding friction force, in magnitude is equal to mu mg. It's always in the opposite direction of motion. I can't say it's always negative. If the object was sliding leftward, then the frictional force would actually be rightward, and that would be considered positive. If it's, as in this case, moving rightward, then yeah, you could say it's leftward. But as soon as you put these absolute value symbols, we're talking quantity, magnitude. We're not interested in the direction. UMG, in the simplest case. All right, how do we fold that directly into this discussion? Because now we have something moving along a frictional surface, just like this one. Right? And I do a little free body diagram up here. The frictional force will be in the opposite direction of its motion, which we know is sliding friction, because it's going to start sliding. We talked about in the last class. It's going to accelerate, assuming that that's the case, that this is an example that involves motion. We know that the gravity force, the weight of the block, is always straight down. And then, again, as was the case before, remember, we knew that the normal force is always perpendicular to the surface. So the surface goes this way, the normal force is perpendicular to that. This is always 90 degrees, perpendicular to the surface, right? So that means, and what a common mistake for students is, for this scenario, drawing the normal force up like this, because they think it's always up. Not correct. It's always in response to however hard gravity is pulling it down, which is the weight of the block, right? And then it responds with an equal amount of force in the upward direction. So for us in this case, perpendicular is going to be in this direction, like this. That's the direction of the normal force, like this. So I would draw it over here like this. Now what we want to do is remember that there are components to the gravity force, the gravitational force, which has a y component and an x component. This is called the y component of the gravity force. This is called the x component of the gravity force, remembering that the x-axis is skewed for these inclined plane problems, so that we consider the x-axis to be right along the surface of the inclined plane, so that all of the block's motion is along the x-axis, slides along this x-axis. We're reducing it essentially to one-dimensional motion by turning our axes, because otherwise it would be considered two-dimensional motion if our x was like this and our y was like this. But now by cleverly going like this, we're reducing two-dimensional motion to one-dimensional motion, since it's just moving along this one axis. But let's refer back to our free body diagram, because we're interested again in usually what is the acceleration down a frictionless, or I didn't mean to say frictionless, a frictional incline. At what rate does it accelerate as it goes down the incline? Well, in the previous class, or previous lesson, we determined that the acceleration rate down a frictionless incline was g sine theta in amount. An example I gave, it was 4.9. If this same 30-degree ramp had friction on it, do we think that the acceleration as it slides down this rough frictional surface would be an acceleration still 4.9 meters per second squared, less than 4.9 meters per second squared, or greater than 4.9 meters per second squared, and why? Well, if there's a roughness on the surface, then that's going to cause some sort of resisting force, kind of slows the object down, prevents it from accelerating as quickly as it wants to, in the case that there was no friction, right? So we would expect an acceleration to be less than 4.9 meters per second squared if it was the same problem, but having to incorporate friction into it. Let's see why. As always, we use Newton's second law to determine the acceleration. We're going to call this x-axis motion. Again, all the motion is along the x-axis. And we're interested in the net x component force. These aren't of interest either because they cancel, right? So maybe I'll make that mark over here on the side. Or make that drawing again over here. Fn and what's called the y component of the Earth's gravity force, effectively the part that's pulling it into the incline and causing pressure underneath here. Those are balanced. They won't come into play when we're talking about the unbalanced amount. The net force is the unbalanced amount. And once again, we've resolved the weight vector into its two components, this one and this one, then we imagine it's gone. And we're trying to seek out the unbalanced amount of force out of 1, 2, 3, 4 forces. Now, I noticed right away just now that my drawing isn't great because according to that, if this one and this one are balanced, and now we're only comparing this one, the frictional force, compared to this one, FGX, I've drawn this one longer than this one, which means I can stick this block down and it will start going up the incline all by itself from friction. We know that's not true. So I didn't really draw that to scale. If I was trying to draw that to scale a little better, which I could actually do probably up here, the frictional force would of course have to be, did I do it too long again? Maybe. Let's see. Yeah, I didn't do a good job at that. Sorry. This is ended up being not the right length. Let's do another try. So I can do this and this and this for the block. It's again sitting there, assuming that this is the incline. But the friction force would technically have to be a smaller amount, right? So that when we say, all right, the normal force and FGY, again, cancel. They're equal in amounts. This one's gone because you resolved it into these two components. These are balanced. You'd say, oh, well, this amount is FGX. Versus the frictional force, which of course would be a little bit less, the sliding friction force. There's a net force, extra amount of force, an unbalanced amount of force in this direction. It would be the difference in how long this is compared to how long this is, but that way, because that's where the extra amount is, right? They have to draw another one right here, and then say those are canceled, and the extra amount is like that, right? That makes sense. So we know that the net force when there's friction is less than when there's no friction. When there's no friction, this represents the net force. As soon as you involve friction, and there's some force in the other direction, that's going to shave off some of this so that the net force is now less than this. And if the net force decreases, what does Newton's second law say about what should happen to the acceleration? Remembering that it states that the acceleration is directly proportional to the net force. So if there's a reduced net force, for whatever the reason might be, in this case it's friction, when comparing it to the frictionless incline, if the net force is reduced due to the effect of friction, the acceleration should reduce in direct proportion. So we would expect the acceleration to be decreased, something less than this one in my last class, my last lesson. Again, if it was all the same, ramp that was 30 degrees, and we calculated that this is the acceleration formula when there is no friction, and it came out as this amount, and then someone said, do the same problem with friction, we know we're going to get something less than 4.9 because of what I had just said. The net force is being reduced because of the effect of friction, right? So how do we now add that in terms of the modeling part? Well, let's see if we can come back to here. Actually, right here, we'll come back to here. So we know that, again, this was the weight. We know that this was FGY. We know that this was FGX. And we know that the normal force in this direction, again, is canceled with FGY. Move that out of the way. I have just indicating that the velocity was down the ramp, but it's kind of in the way right now. So we know that these two canceled, right? And then we had a little, again, here I am with the, not drawing it quite the right length, but it's a little bit of friction. FFK. There's a little bit of friction force. As it slides down, the friction force would be that way, right? But now we have to remember that what I had said before, which is, see if I can find that page, that the sliding friction force, because that's what we have to incorporate now, is this amount of force. The sliding friction force is always equal to the coefficient of sliding friction times the normal force. You can make the argument that the normal force is equal to FGY. So if we can figure out what FGY is in magnitude, then that tells us immediately what Fn is. And if we know what Fn is, then it would be pretty easy to plug that in here and say, multiply it by the coefficient of friction, and we've got an expression for the sliding friction force down a frictional incline. That's where we're headed right now. Let's try. So if we're looking at this image here, right here, and I just blow it up a little bit to make it a little larger because my small drawings become hard to understand, look at, work with. This is just a blown up image of that. Again, and we said this is FG, your weight, total weight. This is FGY, and this is FGX. This was the ramp angle. It's really over here, but remember those are equal. Now we're interested in getting an expression for FGY. We already worked on getting an expression for FGX. Since it was opposite, it went with sine, so it was mg sine theta, because FG is equal to mg. So we already had an expression for the x component, and that's what allowed us to work out the expression for the acceleration down a frictionless incline. We're doing the same thing now, trying to incorporate friction again to work out what is a new formula, what would it be for acceleration down a frictional incline, a frictional incline. So now we have FGY. What would an expression be for it? Well, it's the same thing, right, as we had before. In general, we have to work out whether it's a sine or cosine that matches our component. And it's always the same format, right? The magnitude of the vector times either sine of theta or cosine of theta. We do see that this is adjacent, right? This is adjacent to this angle. And we know that a cosine function provides us with the adjacent, and it also ties in the hypotenuse, which we know, which is mg. Right? So when we're trying to figure out an expression for FGY, we would say, well, it's the length of the hypotenuse, which is mg, which is just the weight, full weight of the object, times the cosine of the angle, because this is an adjacent piece. Right? So this amount of force right here is equal to mg times the cosine of whatever the ramp angle is. This is useful to know, usually, because it allows you to work out, once you know FGY, you can then flip that and say, now we know how much normal force there is, because it's an equal amount, conceptually. This tells us that Fn, if these were just written in magnitudes, ignoring the negative symbols, Fn will also be equal to mg cos theta. I don't know what the numerical value is. It depends on, again, the planet you're on with g. It depends on the mass, depends on the angle of the ramp. This is just an arbitrary expression that can be used for any mass, any planet, any angle. Right? So we have this now. And if we tie this back to our friction topic, the discussion we just having on friction, which I have all these pages all around me, so bear with me, which is here. The frictional force is always the coefficient times the normal force. And we know that this is the normal force. That means I can just slide that expression in for Fn. And you'll see what that becomes now. The frictional force, the sliding frictional force in magnitude, just in quantity, is again the coefficient of friction times the normal force. This is an expression for Fn. So now I have an expression for the kinetic friction force, the sliding friction force, the amount of sliding friction force. If there's no friction, then the coefficient of friction is 0. It means it's frictionless. And the frictional force will be some percentage, because cosine of theta is a percentage of your weight. When there is friction involved, the amount of frictional force, did I say that back? I might have, I don't know what, I think, disregard what I last said. But what I'm trying to say is that when there is friction, sliding friction, you have to recognize that this coefficient provides a percentage of your weight, and so does this, the double percentage, a percentage of a percentage. So it's a small amount. Could be. I mean, it depends again on what the coefficient is. But this expression allows you to calculate what that frictional force is. I mean, in an example, I mean, I don't want to necessarily do it all out, but they would tell you. They'd say the coefficient of friction is 0.20. They'd say the mass of the object sliding down the incline is 2 kilograms. The ramp angle is 30 degrees. Calculate the frictional force. You could certainly plug these numbers in, 0.2, 2, 9.8, cos 30, all into your calculator, hit enter. You can get a number for it. But remember, AP Physics isn't necessarily so much about numbers. It's about modeling, mostly. So this is where we're at. This is where we have to work. So now we can fold this into the net force discussion, right? Because, again, to figure out the acceleration down the frictional incline, we need to know what the net force is. And then it's a simple matter of just dividing it by the mass. All right, well, it shouldn't be too bad. I can find a page of, is there some, yeah, it's underneath me, some extra. So now that we have this here, draw this again. This was FGY. This was FGX. This was mg, the weight of the object. Say this was, again, the block. And this was the little bit of friction force, sliding friction force, FFK. And this would be the normal force. Remember that the net force is the amount of unbalanced force. These are balanced. This one looks a little longer. It's not supposed to be. These are equal amounts. These are balanced. These are out. This one is out because you've already resolved it into these two components. So that means, again, the net force along the x-axis, which goes this way, is conceptually going to have to take into account FGX, and it's going to have to take into account the sliding friction force. It usually makes sense to call the direction of motion plus. It's sliding down, so let's call that plus. And let's call away from the direction of motion minus. You have the right of doing that. So this will be a minus, and this will be a plus. We have expressions for all of these things. FGX was mg sine theta, right? Mg sine theta, that was this piece here. That's the amount of force pulling it down the ramp. What is the frictional force amount? Mu k mg cos theta. Because the mg cos theta is the normal force expression. I like to put mg sometimes in parentheses because it's the weight. So if someone said, what is the net force, right? Well, the net force, if these were just sideways forces, you know it's this amount minus this amount. This is 10 newtons and this is 2 newtons. It's 10 minus 2, it's 8 newtons. But then you're like, well, we don't have numbers. We just have expressions. This is a plus amount in this amount, mg sine theta. This is a negative amount in this expression. Same idea, this minus this. The net force in the x direction should be FGX, is this amount, minus the friction force. And yep, we got these big expressions. Phone call, excuse me. So I end up with FGX, which is mg sine theta, minus mu k times mg cos theta. That's the expression for the frictional force. And it's long. There's a lot of pieces to it. But that's the idea of mathematical modeling. And things can build upon each other, and expressions can get long, but stick with the concepts. Just integrate the expressions with the concepts. The downward force minus the upward force. Yep, we got expressions for the force down the incline, and we have an expression for the force up the incline, which was the friction force. Okay? So finally, we can determine the acceleration. Sure, why my light is kind of giving me issues. Sorry about that. I have a touch lamp here and works, and then it doesn't work, and I'm hitting it by mistake, and then I try to brighten it. Not sure what's going on. Oh, I guess it just stopped working. Right at the right time. Still have enough light here. So now we have, again, this was our expression for the net force. So to finally get the acceleration down the incline with friction, right, it'll be equal to the net force in that direction divided by the mass. What is the net force in that direction? All of this. All of that. Mg sine theta, which again was FGX, mu k mg cos theta, which is sliding coefficient force of kinetic friction, divided by the mass. What happens to m? Cancels and cancels and cancels. And you're allowed to do that when you have two terms on the top and one in the bottom. It's like saying 5 plus 2 over 4 is equal to 5 over 4 plus 2 over 4. So you can imagine breaking this piece into one fraction, 5/4, and then if this is one fraction and there's an m in the bottom and an m top, I can cancel them. And then I would do the same thing for this other piece, 2/4, right? The same thing here. This had an m and it also has an m. It would cancel on that one as well. I don't bother writing that all out. This was just an idea here, math idea. But the m's cancel, which tells us again that the acceleration, even down a frictional incline, does not depend on the mass of the object. What does it depend on? Depends on how strong the planet's gravity is, depends on the ramp angle. That's this part, g sine theta. Depends on how much friction you have in terms of the frictional coefficient. That's being subtracting away, because notice that this g sine theta is exactly what we started with the zero friction. The zero friction case, this is the acceleration down the ramp with no friction. It's still there. And if the coefficient of friction is 0, then this whole term goes away, and you're back to just the first term, g sine theta. But when there is friction, you got to subtract stuff away, because friction always removes accelerations and it removes net force, right? So it makes sense that we're subtracting something here. It depends again on g, depends on theta, depends on the coefficient of friction. Looks like I have another g hiding in here. Cos theta, all divided by m. Could this go one step further? Technically could. If you wanted to stick with like a textbook would then say, well, technically we can factor out a g. That's fine. I don't blame them for wanting to do that. A equals, there's a g here and a g here, so I can factor out a g from both and do sine theta, right? G times sine theta brings me back to this piece. And then if I'm factoring out a g, it would be minus mu k cos theta. Right? So that when I multiply this back out, I'd get mu k g cos theta. Mu k g cos theta, right? All divided by, oh, sorry, not divided by anything. That would have been it, right? Forgetting that we already canceled those out. So interestingly, again, if the coefficient of friction is 0 and it's frictionless, this is 0, this term goes away, and the acceleration down the frictionless ramp is back to g sine theta. There's always some amount of acceleration loss due to the fact that you're sliding down a surface that has friction compared to one that does not have friction, and that's why we have a minus. It has to subtract away something here. All right, I know that that's a lot. I do. And I know that, I'll be honest with you, when I learned this for the first time, I struggled. And I didn't have actually a very good teacher where I was going to school at the time. I was actually at community college. And this was difficult for me, especially with somebody that wasn't explaining anything really that well at all. So I hope that this was in-depth enough. I go through the detail if the student wants to put in the time and wants to understand stuff. I hope there's enough here for you to understand. But even if it's not, just know it takes some time. A lot of this, is kind of challenging for a lot of students because there's a lot of algebraic, abstract representations, manipulations, vectors, trigonometry. I'll be honest, there's a lot going on. Everybody knows that. But stick with it. We'll continue practicing with it in class, and things will get better if you feel like it's still a little challenging. But again, just consider the idea that when you stick with something, no matter what it is, it gets easier, and that will be the case, undoubtedly. All right, hope that was helpful. I will see you guys in the next class.